All right, great. So welcome to the session on proof systems and cryptography. We have 5 exciting talks. And our first one will be on Snark-P from the unprovability of mathematical theorems by Jiechen, Abhishek, Jiatu, and Surya. And Jiatu will do our talk.
Thanks for the introduction, and I will going to explain our recent work on building Snark-NP from a new type assumption, unprovability of mathematical theorem, and I'll explain why. And this is a joint work with Jiechen, Abhishek, and Surya. So modern cryptography have been built on the following standard paradigm. We look for standard assumptions. Usually it's a harness of resolving certain computational tasks like LWE, RSA, so on and so forth. And from them we build like more schemes, a lot of different things like ABE, FHE, PIR, and more things we are building. And of course, it's not the end of the story. We are still building more and more crazy stuff. And to do that, we may look for existing assumptions and find out a clever way of building that. Or maybe sometimes we need to ask for more kinds of assumptions, more kinds of harness structure that cryptographers can utilize. And in this talk, I'm going to explain a new approach to find new harness assumption by viewing the unprovability of mathematical theorems. Unprovability result is actually not a rare thing. It's abundant in mathematics. So the classical result of Gödel shows that as long as you have a nice theory, T, you can always find unprovable statement. The consistency of its own is always going to be unprovable. And also there are a lot of other concrete examples where you have the continuum hypothesis not proven in ZFC, and a lot of other things in modern context, which will be relevant with our work. And at the same time, we also want to mention not only the unprovability result are abundant, unproved results are also abundant. You know, we have a lot of interesting open problems. 7 of them, each of them is $1 million. Only 1 of them is solved. And we have our own problem also. We don't know whether P is equal to NP, NP is equal to co-NP. And my favorite open problem, which is probably a little bit offended if you ask a complex theorist, whether NP is contained in size 6n or not, is wide open. So given all those unproved results, maybe some of them is just because we are not clever enough, like the next GPT will solve the problem, or maybe there is some fundamental reason that you cannot prove them in a weak mathematical theory. And can we use them for cryptography? And what do we exactly mean by using unprovability? We consider this kind of assumptions. You fixed some mathematical theory T, you fix some statement phi, and you want to discuss whether you can prove the statement phi in the mathematical theory T. So it's pretty much similar to like the computational assumption. You have a computational model, you have a problem, you cannot solve the problem. It's the same thing. If you build cryptography based on this kind of assumption, you also get a win-win argument. Either you get a secure construction, or you find a very efficient proof for the mathematical theorem, which is pretty good. You know, we are mathematicians, we love theorems. And of course, we want something more than a win-win. We want a security guarantee. So to tip the scale, we want to make the theory T as weak as possible. So it's more likely that we have cryptography security rather than proofs. In other words, if you break the scheme, you'll get a huge win rather than just adding some small knowledge. And this is more similar to that we prefer harness in polynomial time rather than sub-exponential because it's more likely to be true. And if you break it, it's more striking. So we want weaker assumptions. But here we also want to mention that we want to use some well-established theory rather than some new theory. Because if you just come up with a weird theory that like people don't care about, or maybe we don't have much knowledge, then it's very hard to study. So we want to find a well-established theory so that logicians can get a better understanding and have a better target for crypto analysis. So that's our goal. Find some natural statement, natural theory, use unprovability. We should also mention that we are not the first paper dealing with like unprovability. A very great result of Rahul Ilango showed that you can use unprovability type assumption to construct what he called effective zero-knowledge proof without setup. It's kind of a very crazy result, but you can do it. And our results are inspired by Rahul's approach and similar in spirits. But there's also a lot of crucial difference I will kind of explain. And we encourage readers to like compare these two work. There's some crucial difference. So how do we build cryptography from unprovability? Why it's possible? Why it's good? So I will use the following example to see why you may want to think about unprovability. So imagine that you have some assumption that is widely believed. Let's say NP is not equal to co-NP. So it's kind of a widely believed assumption. And apparently, you find out the negations of the assumption help you to prove security. So if NP equal to co-NP, you can build some crazy thing. So this might happen because it's a very, very strange assumption. It's likely to be false, actually. So if you get a security assuming NP equals to co-NP, what will happen? Well, if you have an adversary, it tells us NP is not equal to co-NP. Usually this is not good. Why? Because people will say that we do believe NP not equal to co-NP, and maybe the scheme is just insecure and there's nothing striking. Right? This is not a security guarantee in general. But one observation is, in this procedure, we know that NP not equal to co-NP, regardless of whether it's true or not, it's going to be hard to prove in some sense. It's not going to be resolved very easily. So the attacker, the adversary, must doing some very, very non-trivial work. So in particular, if you view the security proof, assuming NP to co-NP, as well as adversary, because it will break the security, and you can run the adversary because you have a constructive security game, you combine them, you get mathematical proof of NP not equal to co-NP. So if you actually make the proof very, very simple, so that the proof is unlikely, you actually get a huge win. It's not that NP not equal to co-NP per se, it's you don't have mathematical proof of NP not equal to co-NP. So here you can see that the unprovability of statement gives you the effect of its negation when you do security analysis. You can boost the security assuming NP equals to co-NP to full security using kind of unprovability assumption if you do it wisely. Okay? So go back to our regime. So in this work, we built a new scheme about snarks for NP. So snarks, succinct non-interactive argument, is a proof system for NP, where given a language in NP, the prover want to convince the verifier that some string is in the language, and it will do so by giving a short witness. The witness pi will be much shorter than the NP witness W. So this is not possible in general, so they work in the CRS model where a trusted party set up a CRS for both. And we want it to be correct in the sense that if it is in the language, then the honest prover will convince the verifier. And if it's not in the language, we consider non-adaptive soundness, which means for any dishonest prover, for any string not in the language, over the random CRS, it's very unlikely to convince a verifier. So this is the definition. Fix a prover, fix a string not in the language, it's not going to be convincing. So snark for NP is a very important problem in cryptography because its application in Bitcoin or the cryptocurrency technique, and also because it's a kind of a very natural problem. And there's tons of work in building snarks for NP. So starting from Killian McCallie, there has been a lot of work building snarks for NP from random oracle or knowledge-based assumptions. And in the standard model, we also have a few constructions from mostly indistinguishability obfuscation or witness encryption. Both of them are considered pretty strong assumption, known as offense-topia assumption, pretty strong. And an interesting open problem is, can we build standard model construction outside of offense-topia? Can we use, for example, like LWE or this weaker assumption? They only implies PKE as far as we know to build these kind of things. So our result? So we construct a new snark for NP, assuming these two assumptions. First, we have the standard polynomial security of LWE and SXTH, and we assume for some suitable theory T, it is unprovable for a propositional logic lower bound, extended Frege lower bound. And I will explain what it is. And assuming these two conditions, you can have snarks for NP with non-adaptive security. So what is EF? EF is extended Frege. It's a central proof system in proof complexity, one very natural one, similar to the one you use in textbook. So we are essentially saying that the assumption means you cannot resolve a central open problem in proof complexity in a very weak theory of arithmetic that I will explain what it is. So here, if apparently you don't care about unprovability and you don't like the assumption, there is also one interesting fact about our construction. It seems to be still secure, even if there is no sub-exponential harness. So we don't actually use any sub-exponential security. So in the standard construction, for example, from I/O, if you want to build it from, say, LW, you have to use sub-exponential security in some sense for the complexity leveraging, but we don't use that thing. So it's interesting, even if you don't care about unprovability. So to explain more about what we are doing, I have to give a short introduction of what is proof complexity and what's the status. So proof complexity. So propositional proof system are essentially just non-deterministic algorithm for tautology. It's like I'm trying to prove that certain formula accept all its instances, for all its witness. And because tautology is co-NP complete, we do believe, assuming NP not equal to co-NP, that there is no system that can do it in polynomial size. None of the system is what we call p-bounded, which means it always requires a super polynomial length proof for some tautology. So this is what we believe. So what we know? So this is a picture drawn by Rakha on a lot of different proof systems, and up to now we can prove that below the red line everything is not bounded. But we are working with extended Frege. It's the hardest one over here, and despite decades of efforts, we still don't know how to prove very strong lower bound for extended Frege. So it's a central open problem in proof complexity. So our assumption, in a sense, are saying that you cannot prove extended Frege lower bound, resolving this central open problem in some weak theory. So informally speaking, our assumption will be for all sequence of tautologies, the theory T, which I will specify, cannot prove this psi n is hard against extended Frege. So a small caveat is we need to formalize this in a non-uniform way. It's actually not about like proving, it's about some propositional proof system corresponding to P that prove this, because you have non-uniform adversary, but this is a small caveat. In a sense, it means you cannot prove in the theory that this particular sequence is hard for any sequence. So here, the theory T that we are choosing is actually a very weak theory. It's chosen as a base as a Cook theory PV, which is a mathematical theory in which you can only define polynomial time functions. You're doing math, but you cannot define anything beyond polynomial time. It's a pretty weak theory. And we extend it with two principles. One is a combinatorial principle, and another are like crypto assumptions. And the first two are actually called the theory APC1, introduced by Jiechen, on formalizing probability. It's the weakest Ruber theory to formalize probability and a lot of things related to probability. And it's a weak probability in general, and in particular, it cannot even, we don't know how to prove famous little theorem from it, so it's pretty weak. So why do we think this is a good assumption? We have two observations. First, proving extended Frege lower bound has been proven, like empirically, a hard problem in math. And Rasparov in 2015 actually posed this public challenge, proving this lower bound, even assuming cryptography assumptions. Let's say I allow you to use LWE, I allow you to use Diffie-Hellman, whatever is plausible, prove extended Frege lower bound. And it's open since then. And actually, people thought about the problem long before he proposed this publicly. And here, cryptographic assumption exclude NP not equal to ONP because that will imply any lower bound. So just standard assumptions. And secondly, explain why we actually want to work with PV and this kind of theory. It's like if you remove the thing we added over here and you consider super polynomial lower bound, then it's unconditionally provable in PV. So we have some unconditional unprovability results. So we add a lot of things, of course, but it's still close to where we start. So I can now explain what our result actually is. So we start from a known construction from Jane, Kalai, Lombardi, and Venkutanathan, and they didn't build SNARK for NP, but something slightly weaker. So they show that assuming standard assumptions, there exists a SNARK with the following two properties. It is always correct for any language in NP, and it has limited soundness in the sense that it's not sound for any language in NP, but it sounds for language in NP that has polynomial size extended Frege proof of non-membership. If the string is not in the language, you have certification, and it's actually in extended Frege. So our question is JKLV construction is just a SNARK for NP? So maybe it's just a SNARK for NP. And we actually answered this affirmatively if you assume unprovability. Why? If you can formalize the JKLV limited soundness in a very weak theory T, then the unprovability of EF lower bound will boost the limited security into full security. It's actually a simple observation, like if you have limited security, which shows if you have proof you have security, and you have adversary, then you can prove there is no proofs, no extended Frege proofs. And if you can formalize the first thing in the theory, and you know that by the unprovability result that the last thing cannot be in the theory, the only possibility is that there is no adversary. So you boost limited security into full security over here. But important caveat, this is highly non-trivial to formalize because you choose such a weak theory, and the JKLV paper is such a complicated construction, so you have to be very careful in the formalization. But the point is we want to make a toolchain for cryptography formalization so that in the future, we can be more and more skilled in formalizing more and more different things in a weak theory so that we can construct more crazy stuff using unprovability paradigm. So back to the picture, standard setting, we use adversary and construction challenge to build security and to break some algorithmic harness. And here, we'll view the adversary and some other things as a mathematical proof and break a mathematical proof on probability assumption. Open question, of course, what can we do else with the idea? And you can start with our toolkit and use APC1. So summary, we have unprovability, and we build a general template for doing that. We construct snark for NP via the template, and we get a win-win. Either you have snark for NP, which is pretty good, or you get a very, very efficient answer to Raspberry's challenge. And can we do more? And that's all. Thanks for the attention.
How is it connected to there was a paper recently, or half a year ago, about new standards that are also going to give you some kind of cryptography, and later it was disproved.
Yeah, I think the point is you can use kind of unprovability assumption to boost security into to boost limited security into full security, but sometimes you just have a disproof. I think maybe the disproof can just be formalizing a weak theory, so maybe it doesn't give you any security guarantee. So it really depends on how hard you can formalize that security in, and for our setting, I think it's very comfortable to assume unprovability for extended Frege lower bound. For other theory, you have to study the problem.
One more.
So you said something about Jiechen and Zhang.
Yeah.
I didn't understand, but you said that they proved this, right?
Oh, they prove a weak version of unprovability. They prove the unprovability of super polynomial lower bound in PV. So we consider a very strong extension of PV. You add a lot of things, and we consider unprobability of a fixed polynomial lower bound. So we use a much stronger version than Krajcik and Pudluk. Yeah, that was super.
So can you speculate on what other crypto primitives besides snark you can build using this?
Oh, very good question. So we already have a follow-up result saying that you can use sort of unprovability of incompressibility to build some new cryptography scheme. And also we suspect, for example, when you are dealing with I/O, we also have a very great work of Jing and Zhang. They build I/O for machines with proof of equivalence. So if you can formalize that proof in a clever way, a variant of it maybe, because it itself has some slightly non-standard assumption. So if you can do it cleverly, you can also boost some limited I/O into a full I/O. I think that's one hope.
All right, great. Let's thank the speaker.